Okay, I've got up here on the board another problem that I think of as a wonderful problem. We're going to have S is the portion of this paraboloid, z equals x squared plus y squared, below the plane z equals 4, and it's going to be oriented downward. Now notice, I just said it was the portion of the paraboloid. It's not the paraboloid together with a cap. It's just the portion of the paraboloid. Okay, so it does have a boundary curve. C, which we can write as del S, is the boundary of S, and it's going to be oriented positively with respect to S. So let's see if we can't figure that out. Okay, so I've got this boundary, which is going to be just this circle right here, and that circle is in the plane z equals 4. Okay, and I want to figure out what way we're going around that circle. Okay, well, I'm going to be looking down at it from above. Okay, because I'm going to describe it using clockwise and counterclockwise, so I have to share my perspective with you. Okay, if from above I'm going counterclockwise, my thumb would be pointing up. That's not what I want. But if I flip my hand over, then from above it looks like I'm going clockwise. So that's what we're going to have going around clockwise, where that means this is the front. In case that wasn't clear, that's the front. We're going around clockwise, looking at it from above. Okay, we've got this lovely vector field. I want to calculate the line integral of that vector field two different ways. First of all, as a line integral. And then we're going to use Stokes' theorem and do an appropriate surface integral instead. And believe it or not, we're actually going to do it three ways. It's kind of crazy because Stokes' theorem gives us this equation. There's the left side and the right side. So we're going to do the left side, we're going to do the right side. Then we're going to do a third way. Okay, we'll see. Okay, so if I want to do the line integral, let's do that first. Okay, then I'm going to need to parameterize this curve. So we'll have r of t. Now, one thing that's very important is the curve is in 3 space. It happens to be in a plane that's parallel to the xy plane, so the z value is constant, but the z value is constant at 4. We've got just this curve in a plane, and so sometimes people forget about the z value, and then they run into huge problems because their curve looks like it's in 2 space, but the vector field is clearly in 3 space. So don't forget, even if it's constant, you got to have an x, a y, and a z. Okay. Now, within the plane that's parallel to the xy plane, I'm just drawing a circle. That circle is going to be x squared plus y squared equals 4, because it's when the paraboloid meets the plane. So that's a circle of radius 2. And we said looking from above, we want to go clockwise. And if you think about it, when we look at the xy plane, and we describe clockwise and counterclockwise, we usually are looking from above. If your work is on your desk, you're probably looking down at your desk rather than crawling beneath it and trying to look up through the surface of the desk. So that's the usual perspective that we have, is from above. So clockwise, I would let this be 2 sine t, 2 cosine t. That, I think, is the simplest way to get things to be clockwise. And of course, I'm going to restrict t to being between 0 and 2 pi. All right. So then, the integral along c of f dotted with t ds. Not necessary to put that little loop there, but that just reminds me that this was a closed curve. Okay. I know that that's going to be the integral from 0 to 2 pi. I want to write f in terms of my parametrization. So y squared becomes 4 cosine squared t, x becomes 2 sine t, and z becomes 4. Notice, trying to plug in, if I didn't have a z value, I'd maybe hopefully catch my mistake there. Okay. Dotted with. Now, t is the normalized derivative. I'm going to just dot with the derivative, r prime of t, the non-normalized tangent vector, because the scaling factor that I'm going to get in switching from ds to dt is just the magnitude of r prime. So let's see, r prime of t would be 2 cosine t, negative 2 sine t, 0. All right, so let's just work out that dot product. So I'm going to get 8 cosine cubed t minus 4 sine, yes, minus 4 sine squared t plus 0, and then dt. Okay, excellent. So let's do the integral. I'm going to just write down what f was because we're going to need that again. Okay, so as I copy this up here, I'm just going to do two things. I'm going to split it up into two integrals, and I'm going to rewrite that cosine cubed as cosine squared times cosine. So we'll have the integral from 0 to 2 pi, cosine squared t cosine t dt. Whoops, and there's an 8 there. I'll factor out the 8. Minus 4 integral from 0 to 2 pi of sine squared t dt. Okay, so 8 integral 0 to 2 pi. Rewrite that cosine as 1 minus sine squared t times cosine t dt. I'm going to go ahead and just finish up this integral, and then we'll do this one. Okay, so this would be a quick u sub. Let's let u equal sine t. Then du is cosine t dt. But something very nice happens, because when I change my limits of integration, sine of 0 is 0, and sine of 2 pi is also 0. So I'm integrating over this degenerate integral. I happen to be integrating 1 minus u squared du, but it doesn't really matter what I'm integrating, because since the interval is degenerate, I'm going to get 0. So anything non-zero is going to come from this one. Here, I'm going to be using the double angle formula for cosine. Okay. So I'm going to just remind us, cosine of 2t would be cosine squared t minus sine squared t. Replacing cosine squared with 1 minus sine squared, that's 1 minus 2 sine squared t. Solving for sine squared t is 1 minus cosine 2t all over 2. Okay, so this ended up being 0, so I'm just going to erase it and use this portion of the board. So we've got minus 4 integral from 0 to 2 pi 1 minus cosine of 2t over 2. I think I'm just going to factor out that 2 on the bottom, dt. Quick w sub, let w equal 2t, dw is 2 dt. Now, that's the sort of substitution that a lot of you are going to be comfortable doing in your head. I'm always afraid I'm going to forget a factor of 1/2, so I'm just writing it out. So I would need a 2, which means I'll counterbalance with a second factor of 1/2 on the outside. So all of that's going to cancel. So I've just got negative 1 times the integral from 0 to 4 pi now of 1 minus cosine of u du. So that's negative 1 times u minus sine u evaluated between 4 pi and 0. That's going to be negative 1 times, we'll get 4 pi minus 0 minus 0 minus 0. So we get negative 4 pi. So that's the work integral that we got. I'm going to just write that up here in the upper right-hand corner of the screen. In the next video, we're going to come back and we're going to use Stokes' theorem to evaluate this over the surface that we were given, this portion of the paraboloid.